Thank you for inviting me to give this presentation about what we're doing in Denmark on calcined clay. I'm going to talk about industrial experience with production and use of calcined clay limestone cement. And what you see on this picture is our lovely white chalk, which is our limestone source for the cement production. But apart from the source for the clinker production, actually this limestone, very fine-grained limestone, is a very good filler. And what you see there is actually the quarry at the Aalborg Cement Works with this very nice blue-colored water. So this is how it looks, and this is the main ingredient. And then this is the other main ingredient, and this is also that is Danish clay. This is the Danish plastic clay, as we call it, which is actually a quite widespread clay formations. It is extremely pure. It contains around 90% clay minerals for most of the parts. The clay mineral composition is typically smectitic. Some of these clays are so pure monomineralized smectite that actually they are sold as bentonites. Other clays contain a little bit more kaolinite, a little bit more illite, and we have some horizons with limestone, more marley horizons. But the big things with this is, of course, that it's so pure and it's fairly widespread. The main drawback is it's a swelling clay, so it contains 35% of water. You cannot see it here, but for sure it does. And if you're walking around it, you will soon find out that it's why it's called plastic. You get really dirty, that's the way it is. But anyway, when we were looking for good raw materials, we had to look for what can we get in our country, and this is actually the background for the FUTURECEMTM technology, you can say. And this is, the classical synergy effect, the carboaluminate reaction, which we also found with all raw materials. In this example, which was actually one of the first ones, we by adding a little bit of limestone, a little bit of chalk, we saw this clear synergy effect with 180% relative strength compared to the ordinary Portland cement reference. In our experience, this is a very robust technology. We actually see this as a very, you can say, forgiving technology in a way that it seems to be fairly easy to control in terms of mineralogy, in terms of quality. This is one of the reasons why we actually wanted to go ahead with this and dared to go ahead. I think I'll take a little bit one more picture of our wonderful clay to discuss a little bit about how this came about, because this is not a new development. We, in fact, back in 1991, we started this because at that time we were, you can say, the plant in Aalborg was under attack by some foreign importers, which could offer a cheaper product. So we need to find a way of producing a cheap, high-strength cement. And we tried all sorts of clinker replacement materials: crushed brick, crushed glass, limestone, calcined clay. And that was also when we found that actually mixing the clay and limestone had the synergetic effect. But it turned out that actually the limestone cement was good enough as it was. So we took this, you can say, discovery, this knowledge, and did nothing about it, hid it away, and waited for better times. And those times came when CO2 became an issue, and in Europe, you can say, around 2000, CO2 was actually an issue, and the European Union began the first round of the emission trading system, and there was a lot of worry of high CO2 costs. So this was the reason that we took out this old technology again and began to develop this as a low CO2 cement. And we had the first original FUTURECEMTM project together with our local university here in Aalborg and in Aarhus, Jørgen Skibsels group, and then the geological survey, where we documented technology, surveyed the raw material resources, and applied for this patent, which was then granted in the US and many other places. The next step was then how to research or how to develop the production method for the calcined clay. We ran a project together with FLSmidth, which is an equipment manufacturer. They were developing flash calcination as a calcination method, and supplied their material to cement production, which we of course then could use to make our cements. And the last project, which I'll tell a little bit more about, was this green concrete project, which dealt with how to use the cement. And this was a project which we did in cooperation with, I think that's probably one of the interesting things in this project, that we formed a consortium with the whole value chain of construction. That meant there was cement production, Aalborg Portland, which is the part of Cementir, which is located in Denmark. There's ready-mix producers. We had a contractor. We had consulting engineers. We have the academic institutions, the Danish Technical University for the basic research part, and the Danish Technological Institute for the more research, for the more applied research. And we had even some technical schools in order to teach teach the young people how to use the green cements. And then perhaps the most important thing, we had public building owners, and that was the road directorate, the rail authority, and even the FEMA link, which you can say represent the infrastructure. And the thinking was that if you have a project which will enable the calcined clay-limestone cement to be used in infrastructure, it can be used anywhere. So this was the reasoning. And here are some of the results. And of course, we were looking quite a lot into durability, and I will not say very much about it in this presentation. But I will say that we both did full-scale test, and we did durability testing in the laboratory. For the laboratory side, or for the general, you can say, the standard testing, we found that the limestone calcined clay with this composition had totally comparable durability properties to the conventional Danish concrete, which would be a mixture of OPC and fly ash. The only question marks was carbonation and, to a certain degree, freeze-thaw. Freeze-thaw is perhaps still something sort of riddle. You can easily make good frost-resistant concrete with calcined clay-limestone cement, but it seems that the testing method perhaps not is the most optimal to really understand what is. It's probably too harsh. But the wall there was a full scale, and now it's 7 years old, and you can see it's full of holes, because we use that to test the real properties. And as you can see, just one example, that was the carbonation, which I must say we were very happy about this result, because we didn't see any difference between carbonation of the calcined clay cement and the reference. On this wall, you can also see, because color is one of the issues, which is very often which is, you can say, could be a drawback of the calcined clay-limestone cements. In this case, the color difference is very small. And what I think is most important is that after some time, perhaps weeks, months, the color difference is hard to say, and you have to really know which part of this wall is the calcined clay-limestone cement, and which one is a reference. We made full-scale tests. We made this bridge, or actually, in fact, 4 bridges. We made some walls and floors in the new concrete laboratory at the Technical University. So this sort of gave us a good trust in what we're doing, and also prompted the decision to commercialize the FUTURECEMTM cement. And this is then our commercial drawing of this new cement, which replaces the typical cement used in Denmark, which is an OPC with 5% limestone filler, 5% gypsum, with a cement where a significant part of the clinker is substituted by calcined clay and limestone, up to the 35% substitution, which is allowed by the European cement standard. And what has been very, very important for us is that this is a way of freeing ourselves for the dependence of fly ash. Because in Denmark, we have been very much reliant on coal-fired power production, but as part of the Danish transition, green transition, the coal-fired power stations are phased out. And just for your information, it is the stated goal of the Danish government or the Danish parliament that Denmark shall reduce its CO2 emissions with 70% before 2030. So, of course, everything that can be done in order to help that is needed. So the decision was made to market the cement, but how to produce it. And on this slide, it's just to show you that we are considering for that matter, two technologies, a rotary kiln or the flash calcination that was discussed, what was developed in the previous project. And the rotary kilns has the big advantage that they exist already. And that's also the way we get our calcined clay today. We can buy it at a third party, which luckily has a rotary kiln. But by the end of the day, we want to make our own installation. That will probably be flash calcined. But in fact, and you can see it, it's the amber and the sort of the purple lines, where the one is the flash calcined, the other is rotary calcined. The properties are surprisingly equal. So this is actually really a good thing, which again shows me that this is quite a robust technology, that it's fairly independent on the production technology. The way we produce the cement today in commercial production is actually extremely simple. Here is the calcined clay as we receive it, and then we simply add these nodules to the clinker transport and the gypsum. And everything, all of this is then entered into a ball mill. The limestone is added after the mill, because the limestone we have is actually powder when we get it out of our system. And all this works surprisingly well. It turned out that, and that was in fact the first production trial we made, that we found that we get more or less or very, very similar results to what we got in our pilot, where we had mixed the ingredients, and with our laboratory tests. So it is not. It is actually fairly simple to make this cement in production. I can also say we have used the same. We have produced calcined clay limestone cement at another plant with another mill system, other limestone, other calcined clay, and again here we get the same result, that in fact we got something that was very, very close to the laboratory results. So in a really robust technology. So the new cement was introduced in the market on the 1st of January. We got it certified according to the European cement standard. It was accepted into the Danish concrete standard after passing all the required test, durability and strength tests and so on. And this is then the specification of the cement. And what you can see, it's really like a high strength OPC type. The 1 day strength is a little bit lower, which is fairly normal for a pozzolanic cement compared to an OPC, but the 28 day strength is actually the same. And what is then our experience? This is just to show that, or one example, that the new cement, the concrete made out of this new cement, behaves more or less the same way as traditional concrete. You see, it flows really, really nice, and the stability of the concrete is good. And this is quite normal. We, of course, see that we need to use somewhat more, 50 to 75% superplasticizer, but also, and I'm quite sure that we'll hear something similar from the talks later on today, is in fact that the admixture manufacturers are really good at optimizing their admixtures, and we're very optimistic that by the end of the day, we don't need higher doses of superplasticizers than today. Another surprise we got was actually, and that was really a surprise because we didn't expect that the new cement would be good for precast concrete elements because of the fairly low one-day strengths. But it turned out that when the concrete element producers got the cement, they actually learned how to optimize it. Using accelerators, using little heat, whatever. So actually, they can make good precast elements. They can also make them in an efficient manner. So today we have precast producers which are marketing, you can say, green concrete elements. Right. Introducing a new cement type in the market is not easy. This is not a cheap cement, and of course, it's different from what the customers are used to. So what we see is the drivers for driving change, especially in terms of sustainability, are the big building owners. That could be pension funds, or they could be developers who have a special interest in sustainability. And here's one example. It's a large construction called the UN 17 Village, which is supposed to be made according to the 17 UN Sustainable Development Goals. And of course, the building owner wanted the green cement, and therefore they selected FUTURECEMTM. And we are supplying, or have supplied, these 10,000 cubic meters of ready-mix concrete with the FUTURECEMTM. Some words about the environmental performance. This is cement with an EPD with a global warming potential about 600 kilo CO2 per tons of cement, and that's compared to the OPC, which is 850. We would like to be a little bit lower, but as you mentioned, the Danish clay contains a lot of water, and we need to get that water out, and that of course costs energy. But we don't have the process CO2, so that's why we can make a cement with a lower CO2 emission. But what is important is, of course, how does this behave in a construction? And we have done a number of life cycle analysis of various constructions. And here's an example for an apartment building, where we did the analysis comparing a conventional concrete based on fly ash and OPC with a building made out of FUTURECEMTM concrete, and we could achieve a CO2 footprint reduction of 27%, which I believe is quite good. What of course is also evident in this calculation is a building is not made out of concrete alone. I think very often we are told that concrete is a big sinner in buildings, but you can see, in fact, that 27% reduction in CO2 footprint in concrete is converted into 7% reduction per square meter. It is substantial, of course, but it is only one of the keys to reducing the CO2 emissions, the CO2 footprint of buildings. In conclusion, we're not finished here. The limit right now of the clinker replacement is really the European cement standard, which limits the clinker substitution to 35%. But in a new standard called EN 197.5, there's actually a possibility to go to 50% clinker substitution. So we have started a new project which we call Caliste, along the same, you can say, with the same sort of partnership as we did in the green concrete, with representatives from the whole value chain, in order to develop a cement with much higher clinker substitution, up to the 50%, or with higher early strengths, which, even though the element producers can use the present FUTURECEM, they still would like higher early strengths. So we want to activate the clinker or the clay, so that we get a higher early strengths. And for this, this is what we're going to work with in the next 4 years. And on the perspective is really that by 2030, it is the aim to have FUTURECEM calcined clay-limestone cement as the main cement in Denmark, and hopefully a large production of this will be with the high clinker substitution. So I suppose this was what I had to say. I would like to thank you very much for listening to me, and hope
thank you.
You find this useful.
Yeah, we've got actually quite a few questions for you in the Q&A, and let me go through these. So one of them is just a general question about your thoughts about calcined clays versus natural pozzolans like volcanic tuff and basalt, with respect to environmental impacts and energy consumption required for calcination.
I think with our approach is that you have to do you have to use what you have, and we don't have any volcanoes in our part of the world, but we have a lot of clay. So I think for us this is the natural thing to do. Of course, if you are from in Italy, where they have a lot of tuff, they use this. So and I think that's always natural. So I think there will be a role for all useful pozzolans you can get in large quantities, and you can standardize.
There's another question that follows up on a thought that I had. I was surprised to see the nodules of the clay that you intergrind with the cement clinker. And so there's a question, is it necessary to separate the clay addition from the limestone addition, or can they be interground?
They are, well, yeah, they can easily be interground. It's just because we are so lucky that we get the clay. We can, in our kiln system, the limestone is actually a powder, so we don't have to grind it. But the calcined clay is very, very easily ground. So that works well. And as I told you, at another cement plant, we have tried it where we had to add hard limestone. Limestone is easily ground, and what came out of the mill, which was a mill with a separator, was actually very, very good in terms of particle size distribution.
Okay, and I'll ask one more question, then I know we've got to go on to the next speaker. This is excellent presentation. This is from Cheng He. Have you tried to run a color management through this process? Because it will affect your choice of the raw clays, and also asking if there's any limestone with the clay source.
Yeah, no, we did not run any color control, simply because the color was quite good. The amount of calcined clay we use is fairly limited, and the cementic clay we use do not turn, they're sort of brownish. So then the color is actually quite nice. And as I also explained, is that after some time, the sort of color fades, so you don't really see the big difference between the conventional concrete and the calcined clay limestone concrete.
Thank you so much for such an engaging presentation. It was a good one to start off with. I think it gave a really nice history and overview.